Tonight, we're going to answer a question that sounds simple and turns out to be one of the strangest in all of particle physics. What is a kaon? You've almost certainly never heard of it. It isn't in your body. It isn't in the rocks under the ground or the water you drink or the air anyone breathes. And yet, when physicists first stumbled onto this one small particle, it broke a rule they were sure of, and it forced them to admit that the universe keeps more kinds of matter than anyone had ever counted. The kaon was the first crack in a comfortable picture of what everything is made of. Pull on that crack, and a whole hidden family of matter comes spilling out. Here's what makes it worth your time. This is a particle that lived thousands upon thousands of times longer than it had any right to, and for years nobody could say why. It's a particle that turned out to be carrying a brand new property of nature, one that even the strongest force in the universe is powerless to change. And in one of its forms, it does something that no ordinary object can do. It quietly becomes its own antiparticle, over and over, refusing to settle on being matter or antimatter at all. None of that is a trick of language. Every piece of it is real, measured and confirmed in laboratories many times over. The kaon is genuinely one of the oddest things we have ever found, and the story of how we made sense of it is the story of how we discovered that ordinary matter is only a thin slice of what nature can build. So by the end of this, you're going to understand three things. First, why this particle outlived its own expected lifetime by a margin so wide the words fast and slow stop meaning much. Second, what the hidden property physicists named strangeness actually is, and how it points straight to a kind of matter that is missing from everything around you. And third, how a single kaon can be, in a real and testable way, two opposite things at the same time. There's a detective story shape to how any of this got worked out, and that's part of the pleasure of it. Nobody ever opened up a kaon and looked inside. They couldn't. Everything we're about to say was pieced together from indirect clues, a track that was too long, particles that refused to be made alone, a decay that happened 2 times in 1,000 when it should have never happened. Each clue on its own looks like a small anomaly, the kind of thing you might shrug off. Followed honestly and together, they lead somewhere enormous. This is a story about taking the small, stubborn oddities seriously and letting them pull you all the way down to a hidden layer of reality. And it isn't a piece of dusty history. The very same particle is being made above your head as you listen, studied in machines built to catch the faintest cracks in the laws of physics, and possibly out in the dark between the stars, forming the permanent heart of collapsed suns. One small particle, threaded through the sky, the laboratory, and the densest matter in the universe. That's a great deal to hang on a question that starts with something as small as a smudge on an old photograph. Some of what we'll get to is settled beyond doubt, checked and rechecked in laboratories for half a century. Some of it runs straight into questions nobody can answer yet. Both halves are worth your time, and the kaon is exactly where they meet. Before we begin, if you enjoy questions like this one, make sure to like the video or subscribe. It's a small thing, but it's what helps these quiet deep dives find the other people who like to sit with the universe this way. Now, let's begin. Start with a single photograph, taken in the year 1947. To understand what's in it, you first have to know about the machine that made it, a device called a cloud chamber. Picture a sealed box full of cold, still vapor, kept right on the edge of turning into liquid. On its own, it shows you nothing. The air inside looks perfectly clear, but let a single charged particle race through it, and the vapor gives that particle away. all along the exact path it takes, tiny droplets condense one after another, like the fine mist a cold breath leaves in winter air. A thin line appears out of nowhere and hangs there, long enough to photograph. You're not seeing the particle itself. You're seeing the narrow trail of disturbance it left behind as it tore through. 2 physicists were running these chambers in Manchester in those years, George Rochester and Clifford Butler, and their work sounds almost tedious when you describe it. They photographed the trails over and over, studying the showers of particles that cosmic rays set off. Cosmic rays are just particles from the wider universe, some from the sun and some from far beyond it, and when one crashes into the top of the atmosphere, it shatters into a spray of new particles that rains down toward the ground. To catch the most telling of those particles, the 2 men set a plate of lead inside their apparatus, above the chamber, so that an arriving shower would strike the lead and knock loose fresh secondary particles. Most of what they then saw in the chamber they could name. A gentle curve was a known particle bending in a magnetic field. A straight streak was another. They were building a patient catalogue of the familiar. And there's a quiet romance to where these things came from. No machine on Earth in those years could reach the energies needed to make them on purpose. The energy came for free, out of the sky, in the cosmic rays. When one of those showers slammed into the lead in the apparatus, it could forge a strange new particle right there, in or just above the chamber, and that particle would travel a short way into the gas before it came apart. Rochester and Butler weren't manufacturing anything. They were borrowing the raw power of the cosmos and waiting to see what it made. And every so often it made something nobody had seen before. The photograph that made trouble had a small fork in it, off to one side, well away from everything else. 2 trails springing apart from a single point in the middle of the chamber, and leading up to that point, nothing. No trail came in. Sit with how odd that is. A charged particle leaves a trail. That's the entire principle the chamber runs on. So if 2 charged particles suddenly appear at a point, something had to carry the energy and the motion to that spot. Something travelled there. But that something left no trail at all, which means it had no electric charge. A neutral particle had drifted silently into the middle of the chamber, and then, without being touched by anything, split into 2 charged pieces that flew apart in the shape of the letter V. And here's how thin the evidence actually was. In the paper they published in 1947, out of some 5,000 photographs, just 2 showed these strange forks. Only 2. One looked like a neutral particle coming apart, the other like a charged one. 2 events out of 5,000 is almost nothing, and Rochester and Butler were careful people. They reported exactly what they saw and claimed no more. And what happened next is even stranger. They ran the chamber for another 2 years and found not one further example. It took other groups later, carrying chambers up to mountain tops where the showers are richer, to gather many more of these forks and prove they were a real new class of particle. Because of the forked shape on the plate, they became known as V particles. From the way the 2 visible trails curved in the magnetic field, physicists could work backward to how heavy the invisible parent must have been. And it was heavy. Not as heavy as the proton that sits at the heart of a hydrogen atom, but far heavier than the lightweight particles the cosmic ray sprays usually carried. This was a middleweight, a new object sitting in a gap in the catalogue where nothing was supposed to be. There's a patience in that kind of work that's easy to overlook. No single photograph explains itself. Each one is a frozen instant, a scatter of pale trails, and the meaning has to be teased out by measuring angles and curvatures by hand. Rochester and Butler weren't watching particles live. They were reading the still marks left behind and reconstructing, from geometry alone, what must have passed through. That a whole hidden particle can be pulled out of two trails, and a gap is a small miracle of careful reasoning, and it landed in a strange moment for physics. In those years, the list of known particles was short and felt almost complete. A handful of pieces seemed to build everything. Now the sky was dropping something new into a sealed box, again and again, and it fit nowhere. The particle zoo, as physicists would later half joke, was starting to fill with animals no theory had ordered, and the Kaon was one of the first through the gate. It's a strange thing to hang a whole branch of physics on a smudge in a photograph, but that's genuinely how this began. A mark on a plate, measured carefully, that simply refused to make sense. The people looking at it had no idea yet that they were staring at the first evidence of a hidden kind of matter. They only knew that something didn't add up, and that something wouldn't go away. But here's the thing, the mass wasn't even the strange part. The strange part was hiding in plain sight, in the one measurement nobody thought to be troubled by. It was the distance. That neutral parent had travelled a real, measurable distance across the chamber before it broke, and to anyone who understood how a particle this heavy is normally born, that distance wasn't a small detail. It was the opening of a genuine problem, one that would take years to unravel. So let's talk about that distance, because it's where the whole mystery begins. The particles pouring out of a cosmic ray collision are made by the strong force. The strong force is the most powerful influence in all of nature. It's the grip that binds the heart of every atom and holds the pieces of a nucleus together against enormous pressure to fly apart. When it builds a heavy particle in a high-energy smash, it works with terrible speed. And when a particle made that way is unstable, the same force rips it apart just as fast. The building and the breaking happen in the same breath. How fast is that, really? Fast enough that the particle never goes anywhere at all. A heavy particle that dies by the strong force is gone almost exactly where it was born. In the time it lasts, light itself would cross only about the width of a single atomic nucleus, and light is the fastest thing there is, quick enough to lap the whole Earth many times over in the space of one breath. If even light barely clears the width of a nucleus before the particle is finished, then the particle has gone nowhere you could ever hope to see. It appears, and it's gone, in the same tiny patch of space. The only sign it leaves is whatever it decays into, springing straight from the point of the collision. Picture the strong force, then, as the least patient thing in all of nature. It needs almost no room and almost no time. It reaches across a space smaller than the core of an atom, and it acts. And by the time you could register that anything had begun, it's already over. This is the force that made our mystery particle. This is the hand that should also have unmade it, instantly, in the very same place. Now here's what that particle actually did. It didn't fork at the collision point. It drifted first. It crossed a visible gap, a distance you could measure with a ruler laid on the photograph before it came apart. For a particle that heavy, that gap isn't just large, it's absurd. To travel that far, the Kaon had to survive vastly longer than a strong force death would ever allow. Let me try to put a size on that gulf, because the raw contrast is hard to feel. Imagine you could take the single instant of the Kaon's birth, that flicker in which the strong force would normally have destroyed it, and stretch it out to the length of 1 full second, slow enough to notice and count. On that same scale, stretched by the same enormous amount, the Kaon doesn't live for a second. It doesn't live for a minute or an hour or a year. It has existed for something close to 300,000 years, and the longer-lived kind of kaon would keep going on that same scale for tens of millions of years. The particle outlives its expected end by a margin so wide that the words fast and slow stop sounding like they belong to the same universe. This cuts against something you almost certainly believe, and that belief is usually correct. Heavier particles tend to decay faster. More mass means more energy straining to get out, more lighter particles it can break into, more open doors marked exit. A heavy particle is normally in a hurry to fall apart, and most of them are gone in a flash. Physicists knew this pattern well and trusted it. The Kaon is heavy by the standards of its day, so it should have been among the very quickest to die. Instead, it hung on far, far longer than a strong force death would ever allow, thousands upon thousands of times past the instant it should have been gone. The rule didn't just bend at the edges. For the Kaon, it broke outright. And there's only one honest way out of a contradiction like that. If the Kaon lives far too long to be dying by the strong force, then the strong force simply isn't the thing killing it. Something is stopping the strongest influence in nature from finishing the job it began. The strong force builds this particle in less than an eye blink, and then, having built it, that same force is somehow barred from taking it apart. The Kaon is left sitting there, whole and intact, waiting for some other and far gentler process to come and end it slowly. And there's no room to wriggle out of this. The mismatch isn't a factor of 2 or 10, the kind of small gap an ordinary error might explain. It's a gulf so vast that no reasonable correction could ever close it. When a measurement disagrees with expectation by that much, it's the expectation that has to give. Something in the assumed picture is simply wrong, and the wrongness is pointing straight at the force doing the killing. That's a genuinely peculiar situation, and it's worth being clear about why. The strong force doesn't usually ask permission. It doesn't hold back. It's the bluntest, most decisive force we know. For it to build a thing and then stand frozen, unable to break it apart, is deeply out of character. The strong force acts on this particle constantly. It's the very glue holding it together. What the strong force cannot do is change a certain property the particle carries, a property it's bound to keep exactly as it is. And here's the trap that springs from that. If the Kaon can't shed that property, and there's nothing lighter for it to turn into that still carries the property, then the strong force has no legal move left. It can hold the Kaon, but it can't take it anywhere. So what is this property, the thing the strong force has to keep frozen? The answer turned out to be a brand new feature of matter, one nobody had thought to look for. The first real clue came from a second oddity, one that sat right beside the first. These strange particles weren't rare in the way that hard-to-make things are rare. In the right collision, they came pouring out easily, as readily as anything else in the spray. They were simple to produce. But there was a quiet condition attached to that ease, and it took a while for anyone to notice it was even there. You could never make just one. Whenever one of these strange particles appeared, another appeared with it. They came in twos. A Kaon would emerge alongside a second unusual particle, born from the very same collision, in the very same instant. Physicists could crank up the energy and produce a great many of them, but the strange particles always arrived paired off. A lone one, born by itself with no strange partner anywhere in the picture, was simply never seen. Not in one photograph out of thousands. That kind of pattern has a particular flavour to it, and one physicist recognised the flavour. His name was Abraham Paes, a careful, thoughtful man who had survived the war in hiding in occupied Amsterdam, and he carried that same patience into the way he did physics. Paes looked hard at the pairing and gave it a name. Associated production, he called it, and his idea was simple. these strange particles are never made alone. The strong force can only ever produce them two at a time in matched pairs. He suspected this pointed to some hidden rule nature was quietly keeping, a kind of balance that had to hold whenever these things were created. But Pius only glimpsed the balance. What he didn't yet do was pin down exactly what was being balanced or put a number on it. That final step, the precise bookkeeping, would come a year or so later, and from other hands. To feel why a rule like that forces pairs, picture digging a hole in the ground. You take a spade to a flat patch of earth and you dig. The moment a hollow opens up, a mound of loose soil rises beside it. You can't make the hole without making the mound, because the earth you lift out has to go somewhere. So, a pit and a pile appear together, always, and they're always matched in size. The volume of the hole is exactly the volume of the heap. You can dig a shallow scrape or a deep well, but by no trick and no method at all can you produce a hole with no soil left over beside it. A deficit and a surplus, born in the same act, adding up to no change in the total amount of earth in the world. The new property behaved in exactly that way. The strong force could make it freely, the way you can dig freely wherever you like, but only ever as a balanced pair. One particle came away carrying a positive measure of the new quality, and its partner came away carrying an equal negative measure. Add the two together, and the sum was zero, precisely what there had been before the collision. The strong force had shuffled the books without ever touching the bottom line. That's why a single strange particle, standing alone, was impossible to make. A lone one would be a hole with no mound beside it, a change in the total that the strong force simply isn't permitted to make. There was even a way to put the idea to the test. If strange particles have to be born two at a time, then making them should cost more. A collision would need enough energy to create not one new heavy particle, but a matched pair of them at once. Push the energy past that point, and the strange particles appear together. Stay below it, and none appear at all. That's just what the collisions showed. The balance wasn't a story invented after the fact to explain the pairs. It made a real demand on the world in advance, and the world met it. The partner was usually a particle heavier than the Kaon itself, one of a family that would later be sorted out and given names of its own. But the partner's details matter far less than the sheer stubbornness of the rule. Make a strange thing, and nature hands you a second strange thing in the same motion, whether you asked for it or not. You don't get to order one without the other. The pairing wasn't a tendency or a strong preference. It was absolute, and absolutes in physics are always trying to tell you something. Now hold this second clue up against the first, the long life, because the two aren't really separate puzzles. They're one fact seen from two directions. Something about the Kaon has to stay balanced whenever the strong force is involved, which is why the strong force can only make it in cancelling pairs. And that very same requirement is what ties the strong force's hands when it comes time to destroy a Kaon later. To break one Kaon on its own without its partner present would throw off the exact books the strong force is bound to keep even. So, it can't. It has to leave the Kaon whole and walk away. The pairing rule and the long life are a single mystery wearing two faces, and both of them point at the same hidden thing. There's some quantity carried inside these particles that the strong force is required to keep perfectly level. Nobody yet knew what it was, but they knew it was real, and they knew it was exactly the thing being guarded inside that quiet, drifting track on the photograph. So let's give this hidden property its name, because naming it is where the whole story turns. Two physicists arrived at the same idea from opposite sides of the world. In the United States, there was Murray Gell-Mann, still in his 20s, quick in a way that unsettled the people around him, a lover of languages who collected words and place names the way other people collect stamps. In Japan, there was Kazuhiko Nishijima, working quietly and independently toward the very same rule. Between them, they took the balance that Peirce had glimpsed and turned it into plain bookkeeping. The idea is to give every particle a number. Gell-Mann called the number Strangeness, because these particles had behaved so strangely, and the name was too fitting to shake loose. Ordinary matter, the stuff of you and everything you've ever touched, gets a strangeness of 0. The Kaon gets 1 full unit. Some Kaons carry a strangeness of +1, and some carry -1, and that sign is the whole difference between a particle and its mirror version. Hold on to that detail, because it comes back near the end and quietly changes everything. For now, only one fact needs to land. The Kaon's strangeness isn't 0, and ordinary matter's strangeness is. With the numbers in hand, the rule can be said in a single breath. The strong force has to keep the total strangeness in any process exactly the same from beginning to end. Whatever the books read before a collision, they have to read the same after. Electromagnetism, the force behind light and chemistry and every spark, obeys the same restriction. It too has to keep the strangeness total unchanged. Now notice how cleanly this settles the pairing we just saw. The particles going into a cosmic ray collision are ordinary, so their strangeness adds up to 0, which means whatever comes out has to add up to 0 as well. If the strong force is going to make a Kaon carrying +1 unit, then in the same instant it's forced to make something carrying -1 unit to match. The books have to balance. That's the whole and the mound made exact, written now as a number the force is sworn to preserve. A single Kaon, born alone, would leave the total sitting at 1 instead of 0, and the strong force simply isn't allowed to move that total off 0. This same rule quietly governs which reactions can ever happen at all. Physicists could take two particles, add up their strangeness, and know in advance whether a strong force process between them was allowed or flatly impossible. If the totals couldn't be made to match, the reaction was forbidden, no matter how much energy you threw at it. The number wasn't a description written after the fact. It was a law with teeth, and it never once failed. But here's the part that changes everything, and it's the more surprising half of the rule. The weak force doesn't have to obey it. The weak force, the faint and slow and rare one, is allowed to change strangeness. It can take a particle carrying 1 unit and leave behind particles carrying none. Where the strong force and electromagnetism are bound to keep the tally frozen, the weak force alone is free to move it. It's worth pausing on how two people, half a world apart and unable to easily share their work, reached for the same hidden rule. Nishijima was piecing together the same puzzle from the same scattered clues, assigning the same kind of number to keep the same book's level. When two careful minds invent the same thing on their own, it usually means they didn't really invent it at all. They found it. The rule was already there in the behavior of the particles, waiting for someone to notice, and two someones did. You can picture the whole thing as a simple ledger kept at every collision. On one side, you write the strangeness going in, on the other the strangeness coming out, and for anything the strong force does, the two columns have to match to the last unit. If a proposed reaction would leave the columns unequal, the strong force just won't perform it, no matter how much energy you throw at it. A rule that tells you in advance what can never happen isn't a description written after the fact. It's a law caught in the act of governing. and step back for a second and notice how odd the whole arrangement is. Of the forces that shape the world, the two strongest are forbidden from ever changing this one property, while the weakest is the only one allowed to change it. It's the reverse of what you'd expect. You'd think the mightiest forces would have the most freedom and the feeblest the least. Here, it's exactly backwards. The Kaon's entire strange life, its long wait and its eventual death, hangs on that single inverted rule about which force may change strangeness and which may only preserve it. Sit with how strange an arrangement that is. Two of nature's forces are forbidden from changing this quantity. The third is allowed to change it, and only that third, and it happens to be the weakest and least frequent of them all. Here's a property that the mighty forces must hold perfectly fixed, and only the feeble one may alter. Nature could hardly have designed a stranger division of labour if it had tried, and that single split, which force may change strangeness, and which may only keep it fixed, is the master key to everything odd about the Kaon. So let's follow it all the way down and watch the impossible lifetime turn at last into something that makes perfect sense. Now let's use that one exception to crack the lifetime open, because it explains the whole thing. Put yourself in the Kaon situation for a moment. It's heavy, it's unstable, it's loaded with energy that would very much like to escape by breaking down into lighter, ordinary particles. Every instinct of nature says it should fall apart, and it will, eventually. But to fall apart into ordinary matter, the Kaon has to be rid of its strangeness, because ordinary matter has none. Its own books read 1 unit. The books of everything it wants to become read 0. That single unit has to go somewhere before the change can happen, and here's the trap it's caught in. To break down into ordinary matter, the Kaon would have to lose its strangeness, and the strong force is forbidden from changing strangeness at all. It could, in principle, use the strong force to fall into some lighter particle that still carried strangeness, keeping the books balanced that way. But there's no such particle to fall into. The Kaon is the lightest thing in all of nature that carries strangeness. There's nothing lighter for it to become without giving the strangeness up, and giving it up is the one thing the strong force can't do. Electromagnetism is stuck in exactly the same way. The only force that can erase that unit of strangeness is the weak force, and the weak force is the faintest, slowest, most reluctant hand in physics. It acts rarely. It reaches barely any distance. When it finally does act, it acts gently and late. So the Kaon is stuck. It's fully built and straining to decay, and yet the two quick and powerful forces that could tear apart almost anything else are both unable to change the one thing standing in the way. Only the weak force can free it, and the weak force is in no hurry whatsoever. The Kaon has no choice left but to wait. Picture a traveller stranded on a small island. The island has everything ready for departure. The bags are packed and sitting by the door. The traveller wants nothing more than to leave, but the only boat that ever calls at this island is a single slow ferry, and it comes rarely and on its own schedule. No amount of wanting hurries it along, and no stronger, faster boat is allowed into these waters at all. Until that one ferry appears, the traveller just waits on the shore with the bags packed, going nowhere. When the ferry finally arrives, the departure itself is quick and quiet. But almost the entire story is the waiting. The Kaon is that traveller, and the weak force is the rare ferry. The long lifetime that puzzled everyone is nothing exotic at all. It's a particle sitting on the shore, bags packed, waiting for the only force allowed to carry it away. The strong force built it, and then couldn't unbuild it. So it lingered, whole and ready, until the slow ferry of the weak force finally came. The image is close, but let me be honest about where it bends, the way every analogy does. A real ferry runs on a timetable. You could, in principle, look up when it comes. The weak force keeps no schedule at all. For any single Kaon, the moment of decay is a matter of pure chance, a die quietly rolled again and again until it finally lands. What we call the lifetime is only the average over enormous numbers of them. One Kaon might go quickly, another might wait far longer. There's no clock, only odds, but the heart of the picture holds. Powerful help is forbidden, and the only permitted help comes seldom. It helps to attach a real number to the waiting. A charged Kaon lasts, on average, about 12 billionths of a second before the ferry comes. That sounds impossibly quick, and by the clock on a wall it is. But for a particle of this weight, it's nearly an eternity, longer than a strong force death by a margin too large to picture. In that sliver of time, moving close to the speed of light, a Kaon crosses a real and measurable distance before it comes apart. And that's how the neutral parent could open a visible gap between the point where it was born and the point where it broke. The drift itself leaves no mark. The empty gap between its birth and its death is the whole story. Patience you could lay a ruler against. And it's worth being clear how feeble the weak force really is. Feeble enough that a particle can sit and wait for it across a stretch of time that, on the particle's own scale, is almost unimaginably long. If the strong force is a slammed door, the weak force is a lock that clicks open only once in a great while, at no set hour, with no way to hurry it, and no stronger tool that will do the job in its place. That's why strangeness, once it's made, is so stubbornly hard to be rid of. Nothing quick in all of nature can touch it. Only the slow, rare hand of the weak force can, and it moves entirely on its own schedule. And notice what this does to your common sense about heavy things dying fast. That instinct was never really about weight. It was about how many quick exits a particle has. Most heavy particles die fast because a fast and powerful force is allowed to break them, so they take the first door available and are gone. The Kaon isn't sturdier than those particles. It isn't holding itself together through some special strength. It's simply hemmed in, with every fast door locked, left with a single slow exit that opens only now and then. Its long life isn't toughness, it's a shortage of options. That's the whole answer to the puzzle we started with. But it still leans entirely on that one word, strangeness, as if strangeness were just a rule floating in the world. A rule with this much power over life and death ought to be made of something real. So the honest next question isn't why the Kaon lives so long anymore. It's simpler and deeper than that. What is strangeness, actually? For years, that question had no answer, and strangeness stayed exactly what it sounds like, a piece of pure bookkeeping. Then, in 1964, it got a body. The number worked so well that physicists used it with full confidence long before they knew what it counted. That happens more often in science than you might expect. You find a rule that never fails. You come to lean on it, and only later do you learn what it was quietly describing the whole time. Strangeness kept the books perfectly. It predicted which reactions could happen and which couldn't, and it never slipped. But a number that always balances is still, all by itself, a mystery. Something real had to be doing the counting. The answer came from Gell-Mann again, and at the very same moment from a young physicist named George Zweig, who reached the same idea entirely on his own. Their proposal was radical, and for a while it was genuinely hard to take seriously. The particles that carried strangeness, the Kaon among them, weren't the smallest things there were. They weren't elementary at all. They were built out of even smaller pieces, and Gell-Mann gave those pieces a nonsense word he lifted from a line in a James Joyce novel. He called them quarks. The idea was strange enough that many people first treated it as a bookkeeping trick, rather than a claim about real objects. These quarks would have to carry fractional electric charges, amounts no particle had ever been seen to hold, and stranger still, nobody could knock a single quark loose and catch it on its own. They only ever showed up locked together inside larger particles. It took years of hard experimental work before physicists accepted that quarks are real, physical constituents, and not just a tidy way to organize a chart. But once you accept them, consider what they do to strangeness. Strangeness was never a free-floating rule that nature simply chose to honor. It was a count of a physical ingredient. A particle has strangeness because it literally contains a certain kind of quark inside it. The tally was counting objects the whole time, the way a number on a warehouse ledger, however abstract it looks written down, is really counting crates you could walk over to and put your hand on. The strangeness of the Kaon isn't a label stuck to its outside. It's a piece of matter tucked within. Now feel what this does to the rule from a moment ago. When we said the strong force can't change a particle's strangeness, we were really saying something far more concrete than it sounded. The strong force can't reach in and turn that special kind of quark into an ordinary one. It can move quarks around all it likes. It can bind them and stretch them and rearrange them endlessly. But it can't change what kind of quark a thing is. Changing one kind of quark into another is a power held by the weak force alone, and that's the real reason, right down at the bottom, why only the weak force can alter strangeness. The abstract accounting rule was a shadow cast by a solid fact about what each force can and can't do to a quark. So when you hold a Kaon in your mind now, hold it as a container with a real ingredient inside. Its strangeness isn't a property floating on the surface like a coat of paint. It's the strange quark itself, lodged within, and the whole long life of the particle is the story of that one quark being unable to leave by any quick door. The abstract number we started with has quietly become a thing with weight and a place to be, and it's a good reminder of how physics often actually moves. The rule came first and worked for years, and only later did the object behind it swim into view. The bookkeeping was a shadow, and the quark was the thing casting it. We'd been counting a piece of matter all along, without knowing that's what we were doing. There's a moment in this story that shows just how real the quarks turned out to be. Before many people had accepted them, the patterns they implied were already so regular that one particular slot in a chart sat conspicuously empty, quietly demanding a particle with a specific mass and a specific set of properties that nobody had ever seen. Gell-Mann pointed at the empty slot and said, in effect, there should be something there. Experimenters went looking, and the particle was sitting exactly where the pattern said it would be, with exactly the properties predicted. You don't get that kind of bullseye from a bookkeeping trick. You get it when the numbers are tracking something physically real. And there's a bonus the quark idea threw in. It brought sudden order to the whole sprawling zoo of particles that had troubled everyone for years. Dozens of seemingly unrelated particles, the ones that had made physicists half wish they'd studied something simpler, fell into neat patterns the moment you saw them as different combinations of a few quarks. A mess became a family tree. In fact, the patterns were so regular that a gap in one of them predicted a particle nobody had yet seen. And when that missing particle turned up exactly where the pattern demanded, it was a strong sign the quarks were real. So the guarded thing inside the Kaon, The property the strong force builds with but can never change, finally has a body. It isn't a number painted on the surface. It's an actual constituent, a specific kind of quark that ordinary matter doesn't contain. To really understand the Kaon, we need to meet that quark. So let's meet it directly, because it's a genuinely odd piece of matter. You're already made of quarks, whether or not you've ever thought of yourself that way. Every proton and every neutron in every atom of your body is a tight little bundle of them. And here's a fact that surprises people the first time they meet it. Almost all of that vast interior machinery is built from just two kinds of quark. There's the up quark and there's the down quark, and between them, in various combinations, they make every proton and neutron in every ordinary thing in the universe. Two ingredients, endlessly rearranged, build all the solid matter anyone has ever touched. Both of those everyday quarks are extremely light. They're the featherweights of the quark world, and for a long time it would have seemed reasonable to assume that all quarks were more or less like them, small variations on a single theme. They're not. There's a third kind of quark that follows all the same rules and feels all the same forces, and it sits in the same family, yet it weighs vastly more. This is the strange quark. Measured against the down quark, it isn't a little heavier. It's something like 20 times heavier, a giant standing in a row of featherweights. To feel that gap, picture 3 balloons sitting in a row, each one blown up to exactly the same size. The first 2 are filled with ordinary air, and they drift and bob at the lightest touch. Those are the up and down quarks. The third balloon is identical in size and shape, but it's been filled with water. It sits heavy and low, and it takes real effort to shift it. That third balloon is the strange quark. Same outward form, same place in the row, wildly different weight. Now let me be careful, because that picture can mislead. A water balloon is heavy because of the water stuffed inside it, and you can point to the reason for its weight. The strange quark hides no water and no smaller filling. As far as anyone can tell, it has no inside at all. Its heaviness is simply a property it carries, built into what it is, with no deeper machinery underneath that we've ever found. Why the strange quark weighs what it weighs is a real and open question in physics to this day. The balloon shows you the gap in heft. It can't show you a cause because down at this level, the cause may simply not exist in any form we would recognize. That extra weight, wherever it comes from, changes everything. Heavy things in the quantum world are unstable. A strange quark, left to itself, doesn't want to stay a strange quark. It carries far more mass than the light quarks, and mass at this level is energy waiting to be shed. Given any opening at all, a strange quark will convert into a lighter quark and release the difference as motion and new particles. This is why you don't find strange quarks among the building blocks of ordinary matter. The protons and neutrons in your bones, in the rocks under the ground, in the ordinary body of a star, are built from up and down quarks. Deep inside each of those protons and neutrons there's a fleeting, boiling haze where heavier quark pairs, strange ones included, flicker in and out of existence for the briefest instants, but none of them last, and none are part of the stable makeup of anything you could hold. There's a useful way to feel just how absent it is from your life. Every atom you've ever touched, every breath, every glass of water is built at its stable core from just the 2 light quarks and their electrons. Not one strange quark sits among those permanent building blocks. It plays no lasting part in chemistry. It plays no lasting part in biology. The entire visible world runs without it. And yet, it's a full member of the family, as real as the up and the down, simply too heavy to stay. That's a strange kind of existence to sit with, Here's a piece of matter that's perfectly real and perfectly allowed, and yet never at rest inside anything permanent. It flickers into being in a violent moment and starts dying immediately. The only way to study a thing like that is to catch it in the brief window between its making and its unmaking, and to hold it open in that window long enough to see. You have to trap it inside something. There's a quiet lesson tucked in that too. The world you can see and touch is made only of the parts stable enough to stay. Everything heavier and more fleeting exists just as truly, but never settles, so it never becomes furniture. Reality is larger than the part of it that lasts, and the strange quark is one of the first pieces of the larger part we ever managed to hold still. It's worth being clear about why heavier means shorter lived, because it's the engine under this whole story. In the quantum world, anything that can happen, given enough of a push, eventually does, and a heavy particle is one carrying a large surplus of energy locked up as mass. That surplus is a kind of pressure, always seeking a way to be released into lighter, lower energy pieces. The heavier the thing, the more surplus it holds, and the more routes it has to shed that surplus and fall to something lighter. The strange quark is heavy enough to be desperate to become an up or a down. What saves the Kaon and gives us the time to study it is only that the single force able to grant that wish is so terribly slow. So the strange quark lives a borrowed kind of existence. It can only be created, never simply found. It appears in the high-energy debris of cosmic rays and colliders, and from the moment it exists it's already on its way out, heavy and unwanted, waiting for its chance to become something lighter. The one reason we ever get to study it at all is that, for a little while, it can be held in place. Something can take that fleeting heavy quark and bind it up with an ordinary partner into a package stable enough to drift a measurable distance before it comes apart. And that package built around a strange quark has a name you already know. It's the very particle we've been chasing this whole time, which finally lets us say, plainly, what a kaon actually is. A kaon is one strange quark bound tightly to one ordinary quark of the opposite kind. More exactly, it's a strange quark tied to an ordinary antiquark, or a strange antiquark tied to an ordinary quark. Two pieces locked together by the strong force into a single object. One piece is the heavy, fleeting stranger. The other is a light, familiar partner drawn from the same quarks that build your own body. That pairing, and nothing more, is the kaon. Notice how different that makes it from some of the particles you may know better. An electron is elementary. So is the muon, the electron's heavier cousin. Cut into one of those and you find nothing, no smaller parts, no inside at all. They're points, as far as anyone has ever been able to measure. The kaon isn't like that. The kaon has an interior. It has two constituents you can name, a strange one and an ordinary one, held in a fierce and tiny embrace. When you ask what a kaon is made of, the question has a real answer, and the answer has parts. A particle built from exactly one quark and one antiquark has a name of its own. It's called a meson. The kaon is a meson, and it isn't the only one. The lightest meson of all is the pion, built from nothing but ordinary light quarks, and it carries no strangeness at all. The kaon is the next one up. It's the lightest meson that holds a strange quark inside it. You could think of the kaon as the pion's stranger sibling, the same kind of object with one ordinary piece swapped out for the heavy visitor. There's something quietly profound hiding in that construction. A meson is always a quark bound to an antiquark, which means every kaon holds a piece of matter and a piece of antimatter together inside it. This isn't a figure of speech. A genuine bit of antimatter sits within the particle, clasped to a genuine bit of matter. But here's the subtle thing, and it matters for the whole story. In a kaon, the two aren't the same kind of quark. A positive kaon, for instance, is an up quark, bound to a strange antiquark, two different flavors. Because they're different kinds, they can't simply meet and vanish into pure energy the way a particle and its own exact antiparticle would. They sit together as one overlapping bound state, held by the strong force, in no danger of annihilating each other. So when the kaon finally dies, it isn't because the two destroy one another. It's for a different reason entirely, one we're about to reach. And there's a further oddity in that tiny sealed package. You can't simply open it and take out one quark to examine, because quarks don't come out alone. Try to pull the strange quark free of its partner, and the strong force fights back harder the farther you pull, until the energy you pour in makes fresh quarks rather than releasing the ones inside. The kaon guards its contents completely. The only way it ever gives up what's within is by decaying, all at once, into something new. The heft of the kaon comes from a surprising place too. You might assume that since the strange quark is heavy, the kaon weighs what it weighs because of that quark. But most of a kaon's mass isn't the mass of its quarks at all. It's the raw energy of the strong force straining to hold the two pieces together. That furious binding energy has weight of its own. The quarks supply a part of the total, and the trapped energy of their embrace supplies most of the rest. A kaon is, to a large degree, held together weight, congealed effort. For a sense of the number, a kaon weighs about half as much as a proton, the particle at the heart of a hydrogen atom, and set against the featherweight electron it's enormous, roughly 1,000 times heavier. It's a genuine middleweight of the particle world, exactly as those first cloud chamber measurements suggested. This composite nature is easy to state and strange to sit with. You're used to thinking of particles as the smallest, most basic things there are, the bottom of every list. But the kaon isn't basic, it's assembled. It has an inside with moving parts, a heavy tenant and a light one, wrapped in the fury of the strong force. In that way, it's less like a single solid brick, and more like a tiny sealed room with two occupants who can't be let out one at a time. And all of it happens in an unimaginably small space. The whole kaon, both quarks and the storm of force between them, is bound into a region far smaller than an atom. You could line up an enormous number of kaons across the width of a single hydrogen atom and still have room to spare. The pairing, the weighting, the strangeness, all of it plays out beneath the floor of the visible world, in a space so small the word small stops meaning much. There's a reason the kaon never sticks around, and it isn't annihilation. It's the heavy, strange piece inside. That strange quark, or in the positive kaon, its strange antiquark, is carrying far more mass than it needs, and mass at this level is energy longing to be released. The particle would love to let that heavy piece turn into something lighter and shed the difference, but turning one kind of quark into another is a change only the weak force can make, and the weak force is slow. So the kaon lives on borrowed time, not because matter and antimatter are wrestling inside it, but because its one real exit, the transformation of that heavy, strange piece, is a door that only rarely opens. The wonder isn't that it eventually died, it's that it lasted long enough to be caught and studied at all. So we can finally retire the question we began with, at least as a matter of what. The thing that drifted across the chamber was a strange quark and an ordinary antiquark, bound into a single fragile package, waiting for the weak force to come and take it apart. That's what a kaon is. But a particle isn't only what it's made of, it's also what it does. And this is where the kaon stops being a tidy answer and turns into something far stranger than its parts. Because there isn't one kaon, there are four of them, and the difference between them is the doorway to everything strange that follows. So let's lay them out slowly, because the arrangement itself is the key. Two of the four carry electric charge, one is positive and one is negative. The positive kaon is a strange piece bound to a light piece in one particular arrangement, and the negative kaon is the exact mirror of it, every constituent swapped for its antiparticle. These two are each other's antiparticles, the way a particle and its reflection always are. And for our purposes, they're the simple case. A positive kaon sits on the shore, waits for the weak ferry, and decays. A negative kaon does the very same. They're strange and long-lived, they wait, and then they die. Nothing about them strains the imagination. The other two kaons carry no electric charge at all. There's the neutral kaon, and there's its antiparticle, the anti-neutral kaon. From the outside, they look almost like twins. They have the same mass. They have no charge to tell them apart. If you could somehow hold one in each hand, nothing on the surface would let you say which was which. The only thing that distinguishes them is the hidden sign of their strangeness, that plus or minus we tucked away earlier. One holds a strange antiquark and an ordinary quark. The other holds a strange quark and an ordinary antiquark. Matter and antimatter, swapped, inside an object that wears no outward mark of the difference. Before we go on, let me be clear about what an antiparticle even is, since it sits at the center of everything now. For almost every particle, there's a twin with the same mass and the opposite charges, a kind of perfect mirror image. Bring a particle and its antiparticle together, and they annihilate, converting themselves entirely into energy. Antimatter isn't science fiction, and it isn't rare in these settings. It's simply the mirror version of ordinary matter, and every kaon, as we've seen, already carries a piece of it inside. Now here's why the near sameness of the two neutral kaons matters so much. For the charged kaons, the two versions are held rigidly apart by their electric charge. A positive thing can never quietly become a negative thing. Electric charge is guarded by every force there is, strong and weak and electromagnetic alike, and no process anywhere is allowed to turn plus into minus. So, the positive kaon and the negative kaon stay, firmly separate for their whole short lives. They can never be confused with each other, and they can never become each other. The neutral kaons have no such wall between them. The one thing separating the neutral kaon from its antiparticle is strangeness, that single hidden unit of plus or minus. And you already know the crucial fact about strangeness. The strong force has to respect it. Electromagnetism has to respect it. But the weak force doesn't. The weak force is allowed to change it, which means the one property keeping the neutral kaon and its antiparticle apart is a property the weak force is free to reach in and flip. Sit with what that sets up. The wall between a positive and a negative kaon is built of electric charge, and no force may breach it. The wall between a neutral kaon and its antiparticle is built only of strangeness, and one force is allowed to walk straight through. It's as if two of the four were shut in a sealed vault, and the other two in a room whose one wall is only a curtain. From the outside, the two look the same, but one can be walked through and the other never can. There's a subtlety here worth naming, because it's easy to assume otherwise. Being electrically neutral doesn't by itself make a particle its own antiparticle. Some neutral particles genuinely are their own mirror image. identical to their anti-selves in every respect. The neutral Kaon isn't one of those. It looks neutral and plain, but it carries that hidden strangeness, and its antiparticle carries the opposite. So there really are two distinct neutral Kaons, a matter one and an antimatter one, even though nothing on the surface tells them apart. That hidden distinction, invisible and yet real, is the seed of everything strange that's about to follow. It's worth dwelling on how unusual that makes the neutral Kaon among all the particles we know. Almost everything else is sealed into being itself. An electron stays an electron. A proton stays a proton. Their identities are guarded by charges that no force is allowed to change, so they simply persist, reliably, as what they are. The neutral Kaon has no such guarantee. Its identity rests on the one property the weak force is free to rewrite, which makes it one of the very few particles whose very nature is negotiable. That single crack in its identity is what the rest of this comes down to. So, the charged Kaons, for all their strangeness, live ordinary enough lives. They wait and they decay, and we can set them gently aside. It's the neutral Kaon that carries the real surprise. But before we watch what it does, there's a simpler question we've skipped past. When the ferry finally comes, when the weak force at last reaches a Kaon, what actually happens to it? How does a Kaon die? So let's watch a Kaon die, because it doesn't happen the way you'd guess. When a Kaon decays, it doesn't crack open like a shell to spill out the pieces that were inside. That's the picture most people carry, and it's wrong. The strange Quark and its ordinary partner don't simply come unstuck and fly off as themselves. Instead, the strange Quark transforms. It stops being a strange Quark and becomes a lighter, ordinary Quark, and in that single act of transformation, the whole particle is remade into something else. This is the deep thing the weak force does, the power that belongs to it alone. It doesn't merely push particles around, it changes what a particle fundamentally is. It reaches into the Kaon, takes hold of the heavy strange piece, and converts it into a light quark, shedding the extra mass as a burst of new particles that fly outward. The Kaon doesn't break, it becomes. What leaves the scene isn't the Kaon's old insides, but a fresh set of lighter particles, made new in the very moment of decay. Sometimes those are the little mesons called pions. Sometimes, as we'll see, they're something else entirely. To feel how special that kind of change is, think about the old dream of turning lead into gold. For centuries people tried, with fire and acid and every ordinary tool they had, and every attempt failed. It failed for a reason we now understand. Lead and gold differ in what their atoms are, deep in the nucleus, and no amount of heat or hammering or mixing can change one kind of atom into another. Chemistry rearranges atoms, it can't transmute them. To truly turn lead into gold, you'd have to reach into the nucleus itself and change it, and only a rare nuclear process can do that. It's possible in principle, it's just not a thing fire will ever accomplish. The strange quark faces the same kind of wall. To become a lighter quark, it has to be genuinely transmuted, changed from one kind of thing into another kind. The strong force can't do it, no matter how violently it acts, the way no furnace can make gold. Electromagnetism can't do it either. Only the weak force holds the strange and specific power to change one kind of quark into another. And like the rare nuclear change that could in principle make gold, it happens seldom and slowly. That rarity is the ferry we spoke of, now seen from the inside. The Kaon waits so long to die because transmutation is genuinely hard, and only one feeble force in all of nature knows how to perform it. It helps to know a little about what comes out. When a kaon does turn into pions, those pions are the lightest mesons of all, plain quark and antiquark pairs with no strangeness in them. So, in a real sense, the kaon can shed its strangeness by turning into particles that carry none, handing the extra weight over to motion as the fragments fly apart. Other times, it decays instead into a muon and a ghostly near massless neutrino. Either way, the strangeness that defined the kaon is simply gone afterward, carried off by the transformation. The books return to zero. This power to change one kind of quark into another is the weak force's true signature, the thing that sets it apart from every other force. The strong force and electromagnetism can only push and pull and bind what already exists. They move particles around. They never reinvent them. The weak force alone can reach into a particle and change its very kind, turning one flavor of quark into a different flavor. It's less a force in the pushing sense and more a slow agent of transformation, the one hand in nature that can make a thing into something it was not. And a single kaon doesn't have just one way to die. It has several, and which one it takes is a matter of chance, settled fresh for each particle. One might become 2 pions, another 3, another a lighter particle alongside a neutrino. Physicists tally how often each path is taken, and those fractions are themselves clues to the inner workings of the weak force. But every path shares the same root. In each of them, the heavy, strange piece is transmuted away, and the strangeness that defined the particle is gone, and you can watch the accounting close as it happens. A kaon carries 1 unit of strangeness. Its decay products, the pions, carry none. So in the act of decay, that 1 unit isn't moved or hidden away. It's erased, converted out of existence as the strange quark becomes an ordinary one. The energy that was locked up in the strange quark's extra weight doesn't vanish either. It reappears as the motion of the fragments, flung outward at great speed. Weight becomes speed, and the books that had to stay frozen for the strong force are finally, quietly allowed to change. For the charged kaons, that's the entire story of their death, beginning to end. Inside a positive kaon, the heavy piece is actually a strange antiquark. It waits, and then one day, the weak force transmutes it. And here's a detail that surprises people. A charged kaon most often doesn't turn into pions at all. Its single most common ending is to become a muon, a heavy cousin of the electron, together with a neutrino, with the pion decays following close behind. Whatever the exact products, the strangeness that was there is gone. There's nothing more mysterious to say about it than that. But hold that idea of transmutation in mind, because it has a second and stranger consequence, and it belongs only to the neutral kaons. The weak force can turn a strange quark into an ordinary one on the way to death. By a more roundabout path, that same force can also turn a neutral kaon into its own antiparticle without killing it at all. And that's where the neutral kaon stops resembling anything in ordinary experience. Now let's follow one neutral kaon, alone, from the moment it's born, because it does something no ordinary object can. It begins life as a neutral kaon, with its own definite strangeness, a strange antiquark bound to an ordinary quark. For an instant, it's clearly itself, but the weak force is always present, always faintly at work, and the weak force doesn't respect strangeness. Through a subtle 2-step process, it can flip that neutral kaon into its antiparticle, into the anti-neutral kaon, with the opposite strangeness, and then it can flip it back. Left completely alone, doing nothing, the neutral kaon slides between being itself and being its own opposite. Let that settle, because it truly has no everyday parallel. a thing turning into its own antimatter mirror and back again, over and over, all on its own, while it simply drifts through empty space. Nothing you've ever handled behaves this way. A coin doesn't become an anti-coin when you set it down. But the neutral Kaon does exactly that, because the only thing marking it as matter, rather than antimatter, is its strangeness. And strangeness is precisely the quantity the weak force is free to change. You might wonder how a particle turns into its own antiparticle with nothing coming in from outside to flip it. The answer lives in the weak force's habit of working through fleeting, borrowed states. For a brief instant, the neutral Kaon can dissolve into a shimmer of temporary particles that exist on borrowed time, and when that shimmer settles back into a Kaon, it can settle as the opposite version. No push from outside is needed. The change happens from within, through a quiet flicker of intermediate steps too brief to catch directly. Here's an everyday way to picture the leak. Imagine two rooms that share a doorway, and the door has been left open. In one room, someone is baking bread. At first, the warm smell of it belongs entirely to that room, and you could stand in the second room and notice nothing at all. But the doorway is open, and nothing seals the scent in place, so it drifts. Before long, the smell of baking has crossed into the second room too. Stand anywhere in either room now, and you can't honestly say the scent belongs to one and not the other. It has spread across both, because there was no barrier to hold it where it began. The neutral Kaon's identity leaks in just that way. Its matter nature and its antimatter nature are the two rooms. Strangeness is the doorway, and the weak force is the reason that door won't stay shut. So the Kaon's identity doesn't sit still in one room. It seeps across into the other and back, spreading through both, held in place by nothing. A neutral Kaon that has existed for even a little while is no longer purely a Kaon, or purely an anti-Kaon. It's become a blend of the two, some of each, mixed together in one object. Let me be fair to the image and say where it bends. A baking smell spreads once and then settles, evenly filling both rooms and stopping there. The neutral Kaon is more restless than that. It doesn't spread once and rest. It trades back and forth, matter to antimatter and back again, in a kind of slow rhythm, never coming to a stop. The picture of the open door captures the leaking. It misses the endless rocking to and fro. But the core lesson holds. There's no wall, so identity won't stay put. Take a moment to feel how far this is from anything ordinary. Your reflection in a mirror stays your reflection. It doesn't on its own become you, and then a stranger, and then you again. The neutral Kaon does the equivalent of that constantly, a thing whose reflection and whose self keep trading places, unasked, as a plain feature of existing in a world where the weak force is always faintly at work. And the trading even has a rhythm you can put a number to. A neutral Kaon doesn't flip instantly, and it doesn't dawdle forever. It trades identity on a timescale close to its own lifetime, so that within its short existence it manages to slosh from matter toward antimatter and partway back. Experiments have measured that rhythm precisely, catching the particle in mid-trade. The flipping isn't a story. It's a clocked and countable fact of the world. There's an almost eerie demonstration of the mixing that experimenters can perform. Start with a pure beam of one kind of neutral Kaon and let it fly. Partway along, the antimatter version has appeared out of nowhere, exactly as the leaking predicts. Pass that beam through a slab of ordinary matter, and the blends get reshuffled yet again, because the matter treats the two hidden components differently. None of this should be possible for a particle with a fixed identity. All of it happens, reliably and on demand, in real laboratories. The neutral Kaon's refusal to be one thing isn't a subtlety you have to take on faith. It's something you can set up an experiment to watch. And this isn't some fragile idea that lives only in careful theory. It's been measured directly and many times over. You can make a beam of neutral kaons, let them fly down a length of vacuum, and watch the antimatter version appear partway along where you began with none of it. The leak is real. The mixing genuinely happens. The particle really does trade identity with its own opposite as it travels, and experiments can catch it in the act, which leaves us with a genuinely disorienting question, and it's the one that finally breaks the tidy idea of what a particle is supposed to be. If a neutral kaon is always a shifting blend of itself and its opposite, never purely one thing, then when it finally decays, what exactly is it that decays? Which version dies? The answer to that question upends the tidy list of 4 kaons we just drew up. When a neutral kaon finally decays, it doesn't decay as the neutral kaon, and it doesn't decay as the anti-neutral kaon. Those labels, matter and antimatter, aren't the labels nature uses when it comes time to die. Instead, the decaying particle is always one of 2 specific blends, 2 particular mixtures of the matter, kaon, and the antimatter kaon stirred together in fixed proportions. There are exactly 2 of these blends, and they could hardly be more different from each other. One of them falls apart quickly, the other lingers. The quick blend is gone in well under 1/10 of a billionth of a second, a flash even by the standards of these particles. The slow blend lasts far longer, something like 600 times as long. Same neutral kaon on the outside, 2 utterly different clocks ticking inside, depending only on which blend you happen to be watching. They don't even die in the same way. The short-lived blend tends to fall apart into 2 pions and nothing more. The long-lived blend usually needs 3 pions to decay, or else breaks into a lighter particle alongside a neutrino. 2 different lifetimes, 2 different sets of debris, both coming from what looked, at birth, like the same neutral particle. The difference isn't on the surface, it's in the mixture. And let me be clear about something, because it's easy to get turned around here. These 2 blends aren't 2 new particles smuggled in from somewhere, and they aren't a later stage the kaon turns into. They're there from the very first instant. A neutral kaon born with a definite strangeness is, at that same moment, already a mixture of the fast blend and the slow one. The 2 ways of describing it, by its strangeness or by its lifetime, are 2 different languages for the very same particle, and they simply don't line up. Ask what its strangeness is, and you get one answer. Ask how long it will live, and you get another. When people say a neutral kaon decays as one of the blends, all that means is that the fast mixture, being fast, dies away first and leaves the slow one behind. Nothing waited until the end to be decided. This has a consequence you can actually use, and physicists use it constantly. Suppose you make a beam of neutral kaons and send it flying down a pipe. At the start, the beam is a chaotic crowd of both blends, and the short-lived one is busy dying off almost immediately. Travel a little way down the pipe, and the quick blend is essentially all gone, burned away, leaving behind a beam made purely of the long-lived kaons, all ticking to one slow clock. You've sorted particles not with a magnet or a filter, but with nothing more than distance and time. The universe does the sorting for you, for free, just by letting the fast blend die away. The size of the difference between the 2 blends is larger than it sounds. The patient blend outlasts the hasty one by roughly 600 times. Put a human scale on that. If the fast blend lived for a single heartbeat, the slow blend would keep going for roughly 10 minutes. Same particle at birth, and yet one is gone in a blink, while the other lingers on, and nothing about a freshly made neutral kaon tells you which of the two clocks it will end up keeping. This double lifetime isn't a laboratory curiosity tucked into a footnote. It shapes how every experiment with neutral kaons is built. Physicists choose where along the beam to place their detectors precisely because they know the fast blend will be gone by a certain point, and the slow blend will remain. The strange arithmetic of the two clocks becomes a practical tool, a way to hand yourself a clean sample of one kind of particle just by choosing where to look. Nature's refusal to give the neutral kaon a single lifetime turns into something you can build with. There's something almost paradoxical in it. The versions with a clear identity have no clear lifetime, and the versions with a clear lifetime have no clear identity. You can pin down what a neutral kaon is, or how long it lives, but the particle won't let you pin down both at once. That trade, identity for lifetime, isn't a quirk of these particles. It's a deep feature of how the quantum world is put together, and the kaon shows it more plainly than almost anything else. And the two blends don't just die at different speeds, they die into different things, which is how you tell them apart in the first place. Catch a neutral kaon breaking into two pions, and you've almost certainly caught the fast blend. Catch one breaking into three, or into a lighter particle and a neutrino, and you're watching the slow one. The decay itself announces which mixture you had. It's as if the particle kept its true nature secret right up until the final instant, and only confessed it in the way it chose to fall apart. So which one is the real kaon? Is it the matter version and the antimatter version, the two you can label by their strangeness, but which never hold still? Or is it the two blends, the short-lived and the long-lived, which have real lifetimes but no definite answer to whether they're matter or antimatter? Both descriptions are correct, both are complete, and they aren't the same list. The particle has two different, equally valid identities, and you can't hold both in focus at the same moment. To understand what that even means, we have to let go of a very old assumption about what a particle is. We tend to assume, without ever deciding to, that a particle is a little object with a fixed set of properties. It has a mass, it has a charge, and surely we think it's either matter or antimatter, one or the other, with a definite answer written on it somewhere even if we can't read it. The neutral kaon quietly refuses this whole picture, and it's been refusing it for decades. So let's talk about the colour purple, because it's the closest everyday thing to what the kaon is doing. Go looking for purple in a rainbow, and you won't find it. The rainbow runs from red at one end through to blue and violet at the other, each band a single pure colour of light, and purple isn't among them. There's no single ray of light that is purple, and yet you see purple constantly on flowers and fabric and screens. So where does it come from? Purple is what your mind produces when red light and blue light arrive together at the same time. It isn't a colour of light in its own right. It's a blend, reported by your eye, as though it were one thing. Now ask the question that sounds reasonable, but is secretly confused. Which single wavelength of light is purple, really? The question has no answer because it rests on a mistake. Purple isn't a hidden single colour waiting to be identified. Purple simply is the combination of red and blue. To demand that it be one pure wavelength underneath is to misunderstand what purple is. The blend isn't covering up the real answer. The blend is the real answer. The neutral kaon is like purple. The matter kaon and the antimatter kaon are its red and its blue, the two pure ingredients. But the particle that actually flies and waits and decays, the neutral kaon as it lives in the world, is a blend of the two. And the question everyone wants to ask is it really matter or really antimatter, is exactly like asking which single wavelength purple really is. It has no answer, because it rests on the same mistake. The Kaon isn't secretly one or the other. It genuinely is the mixture. The blend is what it is. Let me be careful, because purple and the Kaon aren't quite the same kind of blend. Purple is a fact about your eye and your brain. Take away the observer and there's no purple, only red and blue light travelling separately. The Kaon's blend isn't like that. It's out there in the particle itself, with or without anyone watching. It's more real than purple, not less. The mixture genuinely lives, genuinely flies, genuinely decays as a unit. But the lesson the two share is the one that matters. Asking which pure thing it truly is can be the wrong question, built on an assumption the world simply doesn't honour. There's a matching pair of viewpoints hiding in the purple picture, and it's exactly the Kaon situation. You can describe light by its pure colours, red and blue and all the rest. Or you can describe what the eye reports, blends like purple included. Both descriptions are complete, and neither is wrong, but you can't use both at once to name a single patch of light, because they carve the world up in different ways. The Kaon has the very same doubleness. You can describe it by its strangeness as matter or antimatter, or by its lifetime as the fast blend or the slow one. Each description is whole on its own. They just don't line up, and no particle is required to satisfy both at the same instant. This is why the Kaon feels so slippery, and why the slipperiness isn't a gap in our knowledge. We keep wanting the particle to have one master identity underneath, a single true answer we could reach if we only looked hard enough. The particle keeps declining to have one. It offers two complete descriptions that won't merge, and it lets you pick whichever the question in front of you needs. What it never does is hand over a single fixed self beneath the two. There's no beneath. The two descriptions are the whole of it, and that isn't a limit on what we can know. It's a fact about what the thing is. And that's the quiet lesson this one particle has been carrying the whole way down. A thing can be a genuine mixture. Which one is it can be a question with no answer, not because we lack the tools to look, but because the question assumes a single answer the particle was never obliged to have. We started out asking what a Kaon is, expecting a single fixed object with a label on it. What we found instead was a particle that holds two complete descriptions at once, neither one hidden underneath the other. That isn't a gap in the physics. It's the physics telling us our expectation was too small. And notice that this isn't unique to the Kaon, even if the Kaon shows it more vividly than almost anything else. The same refusal to hold a single definite value until the final moment of measurement runs all through the quantum world. The Kaon is simply a case where the two possibilities are as stark as matter and antimatter, and where the blur lasts long enough and travels far enough that we can catch it out in the open. It's a large, slow, visible example of something the smallest pieces of reality are quietly doing everywhere, all the time. And so we arrive at the strangest and truest way to answer what a Kaon is. A neutral Kaon isn't a thing with one hidden identity waiting to be uncovered. It genuinely is the blend. Ask for its strangeness, whether it's matter or antimatter, and that's a real question with a real, shifting answer. Ask which of the two lifetimes it carries, and that's a different real question with its own answer. The particle honours both and belongs to neither, not out of mystery or ignorance on our part, but because holding two overlapping natures at once is simply what it is. And that same blend was hiding one more secret, the deepest one of all. So let's turn to that secret, the one that made this humble particle famous. For years after the mixing was understood, Physicists believed the two blends respected one last symmetry, a deep balance between matter and antimatter. The belief was reasonable, and every experiment supported it. It came down to this. Whatever differences the matter Kaon and the antimatter Kaon had, they were supposed to cancel so cleanly that the long-lived blend would never decay in a certain forbidden way. In particular, the long-lived Kaon was expected to fall apart into 3 pions, but never into just 2. 2 pions were off-limits to it, ruled out by the symmetry everyone trusted. In 1964, a careful experiment set out to confirm exactly that. James Cronin and Val Fitch, together with their colleagues, took a long beam of neutral kaons, let the short-lived blend die away, and studied what was left. What was left should have been pure long-lived kaons, decaying only into 3 pions, never 2. The team watched patiently, and in a tiny fraction of the decays, about 2 in every 1,000, the long-lived Kaon did the forbidden thing. It fell apart into 2 pions. It's a small number. 2 parts in 1,000 sounds like almost nothing, but it should have been 0, and it wasn't, and that difference turned out to be one of the most important small numbers in the history of physics. It meant the symmetry between matter and antimatter wasn't perfect after all. The mirror was flawed. Matter and antimatter, which everyone had assumed were exact reflections of each other, behaved just slightly differently, and the neutral Kaon was when nature first let that difference show. Here's a way to feel it. Picture 2 prints made from the same photographic negative. You lay them side by side and they look identical, the same image down to the smallest grain, and you'd swear they were the same picture. Then you notice, in the corner of one, a single tiny speck that the other doesn't have. Everything else matches, but that one speck means the 2 aren't truly identical, and once you've seen it, you can't unsee what it implies. The Kaon's forbidden decay was that speck. It was proof that matter and antimatter aren't flawless copies of one another. Cronin and Fitch didn't set out to overturn a symmetry. They expected to confirm it. When the 2 pion decays kept appearing, their first instinct was the right one for careful people. They suspected their own apparatus, some stray contamination, some flaw in the beam. They checked and checked again and hunted hard for the error. The error wasn't there. The effect was real, and it was the universe breaking the symmetry, not the equipment. Sometimes the most important discoveries arrive disguised as a mistake you can't manage to get rid of, and the smallness of the effect is part of its power. A large, obvious asymmetry would have been spotted long before and folded into the theory from the start. This one is so slight that it stayed hidden until an experiment went looking with real care. That's often how the deepest features of nature show themselves, not in a loud break, but in a faint, stubborn discrepancy that won't go away no matter how hard you try to explain it off. The Kaon's 2 in 1,000 was exactly such a discrepancy, and physics has been chasing its full meaning ever since. It's a heavy thing to hang on 2 pions out of 1,000, but the number was solid, checked and rechecked, and it has never gone away. The neutral Kaon meant it, and it's still one of the sharpest windows we have onto the difference between matter and its mirror. It's hard to overstate how unsettling that tiny leak was at the time. A perfect balance between matter and antimatter had felt almost necessary, the kind of symmetry the universe surely had to keep. The Kaon showed that it didn't, and if the 2 had stayed flawless mirrors, they might well have cancelled each other completely in the first moments of the universe, leaving nothing behind but cold light. The fact that there's matter here at all, that there's a universe of stars and rock and people, rather than empty radiation, may trace back to exactly the kind of imbalance the Kaon first revealed. And the leak didn't close the book. It opened one. A tiny, real difference between matter and antimatter demands an explanation, and the explanation buried in the known laws turns out to be far too small to account for the lopsided, matter-filled universe we actually live in. So the Kaon didn't just reveal the crack, it revealed that the crack we can see isn't wide enough, that there must be more to the story of why anything survived at all. Decades later, physicists are still chasing that gap, and the neutral Kaon is still one of the places they go to look for it. I won't follow that thread all the way here, because it opens into one of the largest questions there is, the question of why the universe is made of matter at all rather than nothing. That's its own long story, but it belongs to the Kaon, and it should be said plainly. The particle that wouldn't hold a single identity, the one that drifts and blends and refuses to choose, was also the very first place the universe admitted that its two halves, matter and antimatter, aren't exactly equal. That tiny imbalance may be part of the reason there's anything here at all. The discovery earned Cronin and Fitch the Nobel Prize, and it came out of that same neutral Kaon, still giving up secrets long after anyone expected it to have any more. Now let's step back and ask what this one small particle opened up, because it's far more than itself. Think about where we've arrived, and let me be careful with the history, because it's easy to tell it backwards. When Rochester and Butler caught that fork in 1947, nobody had any idea what a quark was. The whole idea of quarks was still 17 years in the future. So at the time, no one could say the Kaon contained anything called a strange quark. All anyone knew was that they'd found a new particle behaving in a way the known rules couldn't explain. The meaning only came into focus in 1964, when the quark model finally arrived. And it didn't arrive by adding a strange quark to a settled pair of up and down. It proposed all three at once, up and down and strange together, as the first members of a brand new kind of building block. Only then, looking back, could anyone see what that first fork had really held. For 17 years, the Kaon had been carrying the earliest evidence of strangeness, a whole kind of matter with no lasting place in any rock or any ordinary star, and nobody had possessed the idea needed to recognize it. That's the true weight of the discovery. Matter comes in more kinds than the world we can see ever bothers to show us, and the Kaon was the first hint that this was so. Physicists have a word for these different kinds of quark. They call them flavors, a deliberately plain and slightly playful word for something with no taste at all. Up, down, and strange were the first three flavors of the new model, and strange was the one that doesn't build ordinary matter. And once that model was in place, an obvious question followed close behind. Were three flavors the whole of it, or were there more heavy cousins waiting, just as absent from ordinary matter, just as real when made? There were more. Over the decades that followed, the family filled in. A heavier quark called charm, then a heavier one still called bottom, then the top quark, the heaviest of them all by a wide margin, each one a sibling of up and down and strange, following the same rules and feeling the same forces, and each one absent from the stable makeup of your body and your world. A whole further layer of matter, there all along, revealed only when collisions grew violent enough to make it. And there's a shape to that family that hints at something deeper still. The heavy quarks didn't arrive at random. They seem to come in matched sets, echoing the light pair that builds ordinary matter, as though nature had made more than one copy of the same basic design at heavier and heavier scales. Why it should do such a thing, why the pattern repeats at all, is a question physics still can't fully answer. The strange quark was the first clue that the repetition was even there. It's easy looking back to make the discovery sound tidy and inevitable. It was neither. For years, the strange particles were a source of confusion and argument, a mess of trails and numbers that stubbornly refused to resolve, and the people who untangled it were working right at the edge of what anyone understood, guessing and revising, and often simply wrong. That the tangle finally straightened into something as clean as a new kind of quark is a testament to how much order can hide inside apparent chaos, waiting for the right idea to bring it out. And the discovery quietly reframed an assumption everyone had been making. People had taken the everyday world as a fair sample of what exists, as if the matter around us showed the full range of what matter could be. The strange quark said otherwise. The ordinary world is a narrow window. It shows only the lightest, most stable options, the few parts steady enough to build lasting things from. The heavier kinds are just as real. They're simply too fleeting to settle into rocks and rivers and bodies, so the everyday world never puts them on show. The Kaon was the first proof that the window was narrow, that there was far more out there than the view from inside it ever suggested. There's a pattern in science that the Kaon shows off perfectly. A single stubborn anomaly, taken seriously, opens onto far more than itself. Nobody set out to discover a new kind of matter. They set out to explain why a particle in a photograph lived too long, following that one thread honestly, refusing to look away from the thing that didn't fit, led step by step to strangeness, then to quarks, then to a whole hidden family of matter. The universe seems to reward that kind of stubborn attention. It hides its largest secrets inside its smallest inconsistencies and waits to see who keeps looking. It's worth sitting with that plain word, flavor, because it carries a real idea under its lightness. The quarks don't differ in shape, and they don't differ in the forces they feel. They differ mainly in mass, and in this single tag we call flavor, a kind of identity that only the weak force can change. The strange quark and the heavier flavors after it are the same instrument as up and down, just built in heavier and heavier weights. Same strings, same rules of play, wildly different heft. The Kaon was where nature first sounded a note from outside the two light flavors that build the everyday world. So the Kaon was the doorway to all of it. That quiet, forked track on a photographic plate wasn't just the first strange particle. It was the first evidence that the universe keeps more kinds of matter than the everyday world ever puts on display. And the story didn't stop back in those years. These particles are being born right now, in enormous numbers, in places both far above you and close at hand. So let's bring it into the present, because the Kaon is anything but a museum piece. The same process that first made Kaons is running continuously, everywhere, all the time. High in the upper atmosphere, particles from deep space are striking the air constantly, just as they struck it above that Manchester laboratory. Each collision sprays out new particles, and among them, in great numbers, are Kaons. They aren't rare visitors. The upper air is quietly manufacturing them without pause over every part of the Earth. Most of those Kaons never reach the ground. They do exactly what this whole story has shown them doing. They wait briefly on the shore, and then the weak ferry comes and they decay, high overhead, into lighter particles. Those lighter fragments crash onward into more air and make still more particles, a cascade tumbling down through the sky. Some of what finally reaches the ground and passes gently through your body wherever you happen to be, traces its family line back up to a Kaon that lived and died a dozen miles up. In a quiet and continuous way, you're standing in the fallout of strange particles being born far above you. The numbers overhead are large in a way that's easy to say and hard to feel. Every hour, across every stretch of sky, a great many Kaons are being made and are dying in the upper air. They've been doing it for as long as the Earth has had an atmosphere, and they'll go on long after us. The forked track that once seemed a rare curiosity in a sealed box was a single caught glimpse of something happening ceaselessly, everywhere above the ground, in enormous abundance, and we don't have to wait for the sky to make them anymore. In accelerators on the ground, physicists now produce kaons deliberately, in clean and controlled beams, and they study those beams with a precision that would have stunned the people who first puzzled over the forked trails. They follow the neutral Kaon through its trading and its rare decays, and pin down the results to a fineness that borders on the absurd. The reason for all that care is simple. The Kaon has broken a rule before, and a particle that has surprised us once is exactly where you go looking for the next surprise. If the known laws are hiding anything, the neutral Kaon is one of the most sensitive places in all of physics to catch the flaw, so we keep watching it closely, decade after decade. There may even be places where strange quarks aren't fleeting at all. Deep in the crushed core of a neutron star, where matter is squeezed past every ordinary limit, the pressure may grow so extreme that strange quarks become a permanent part of the mix. In that setting, the strange quark wouldn't be a brief visitor made in a collision and gone in a flash. It might be ordinary furniture, a standing ingredient of the densest matter in the universe. We aren't certain. It's one of the genuine open questions about what lies inside those stars. But it means the strange quark, so absent from your everyday world, could be a bulk building block somewhere out in the dark between the stars. Bring it closer still. The thin rain of particles from the sky is passing through your body without pause, a soft, constant sleet you never feel. A small part of it carries, somewhere back in its family history, a Kaon that lived and died high overhead. You aren't separate from any of this. The same process that once filled a physicist's sealed box is unfolding in the space your own body takes up, quietly, every second of your life. And the watching isn't idle. Every so often a hint surfaces in the Kaon data that some decay happens a touch more or less often than the known rules predict. Most such hints fade under closer study, but each one is taken seriously because the Kaon has earned it. It was the particle that revealed strangeness, and the particle that first cracked the mirror between matter and antimatter. If a fourth surprise is waiting somewhere in physics, few would be shocked to find it, once again, hiding inside a neutral Kaon. There's something fitting in that continuity. The particle that first arrived unannounced, out of the sky, refusing to obey the rules, is still the one we trust to tell us when the rules are incomplete. It came to us as a gift from the cosmos, long before we had any machine capable of making it, and even now, with all our accelerators, the sky still makes far more Kaons than we ever will. We didn't summon this particle into physics. It fell in, and we're still learning to read what it brought. And the effort to catch the Kaon out is anything but casual. There are experiments whose entire purpose is to watch for a single, spectacularly rare Kaon decay, one expected to happen only a handful of times in tens of billions of chances, because the exact rate is a razor-sharp test of the known laws. Teams spend years building detectors and sifting data for those few events. It sounds absurd to pour that much care into something so rare, until you remember what the Kaon has done before. This is the particle that broke 2 rules already. If it's going to break a third, that faint decay is one of the likeliest places the break will show. So the Kaon reaches across the whole span of the cosmos. It's made in the air overhead. It seeds the thin rain of particles that drifts down through you. It's captured and questioned in machines built by human hands, and it may live in permanence in the hearts of collapsed stars. The strange quark that ordinary matter left out turns out to be woven quietly through the sky, the laboratory, and the deepest cause in the universe, not absent at all, just hidden in the places we rarely think to look. And so we come back to where we began, to that single photograph from the year 1947, a small forked mark, 2 thin trails springing from a single point and nothing leading in. For years it was a puzzle without a solution, a track that travelled too far and lingered too long. You can understand it now for exactly what it was. It was a strange quark, bound to an ordinary antiquark, made in an instant by the strongest force in nature. It was a particle sitting patiently on the shore, whole and ready, waiting for the one slow force allowed to take it apart. And if it was one of the neutral ones, then even as it drifted, it was quietly trading its identity with its own mirror, matter and antimatter, back and forth, a question the universe hadn't yet closed. All of that held in a mark small enough to miss on a single photograph of the sky. And the same thing is happening far above you as these words reach you. Kaons are being born in the high air, drifting their brief drifts and waiting their brief waits, blending and trading and coming apart, seeding the soft rain of particles that falls through your body without your ever feeling it. The strangeness that took physicists a decade to name is sifting down through you, quietly and endlessly, from the sky. But the deepest thing the Kaon leaves you with isn't a fact about quarks at all. It's a gentle correction to how you picture the world. We tend to think everything has to be some definite thing, that underneath it all there's always a single plain answer to what is this really. The Kaon says otherwise, and it says it without drama, just by existing. Here's a particle that genuinely doesn't hold a single identity, that lives as a blend of matter and antimatter, that answers the question of which it is only in the last instant of its life. Asking it to be just one thing was our assumption, never its promise, and it leaves us standing at an honest edge. We can say what a Kaon is and what strangeness is, and we can measure all of it to a staggering precision, but we still can't say why nature bothered to make heavier copies of the everyday quarks, why strangeness exists at all, or the whole hidden family that came after it. The Kaon pried open a door we still haven't walked all the way through, and that unanswered why isn't a failure. It's the part still waiting for someone to be curious enough to chase it. So the answer to the question we began with, what a Kaon actually is richer than any single sentence can hold. It's a strange quark and an ordinary antiquark. It's the lightest carrier of a hidden new kind of matter. It's a small clock that waits for the weak force, and in its neutral form, it's a thing that won't settle on being only itself. All of that is true at once, and all of it lived in that one faint fork on an old photograph, waiting years for someone patient enough to read it. And it's worth remembering how it all started, not with a grand theory or a giant machine, but with 2 patient people photographing the sky and the willingness to be bothered by a single track that went a little too far. That's often all a doorway into something enormous ever is, a small thing that doesn't quite fit, and someone unwilling to look away from it. None of this asks anything of you. The Kaons fall whether or not you know they're there, whether or not anyone ever photographs another one. But knowing changes how the quiet feels. The empty air overhead isn't empty, and the plainest question you can ask of anything, what is this really, turns out to have no simple flaw. The universe kept more kinds of matter than we ever counted, and hid them in plain sight above our heads. And it built into one small particle falling from the sky, a quiet refusal to be pinned down to a single answer. That's what was waiting inside that forked mark all along, for anyone awake enough to wonder about it, wherever and whenever they happened to be listening.